key aspect in creating any sort of control chart is to be able to create the upper control limit and the lower control limit. And the overall pattern here is going to be that you're going to calculate the mean of whatever statistic that you're working with. In this case it's Xbar, and you're going to add and subtract, and typically 3 standard deviations of that statistic. And so that might be 3 sigma x bar in this particular case. And remember that for us, sigma x bar is sigma x over square root of n. Right? And our center line then, in general, is going to be just simply located where our mean is. However, in general, or we can soft that and just say often, we do not know either one, mu or sigma. So the question becomes, well, how do we estimate that? And there's of course some natural approaches to that are going to get adjusted slightly for our specific instance here, and that is that our estimator for the mean is going to be a fairly natural value. It's going to have a weird symbol, so I'm going to leave that blank here for a moment. We're going to take all of our data points that we have, right, and remember that those are not individual samples, but those that we're plotting are actually the sample means for each of our subgroups. And so we're going to sum those up and find their average. So crucial here in our notation, particularly that coming from Montgomery and Runger, is that M is your number of subgroups and N is the sample size in a subgroup. Right? And there's a special case of N equaling 1, but we'll deal with that at another time. Right? For our concrete example, our sample size was 3. Right? And so what we're doing is taking the average of a bunch of averages. And so that's why one of the symbols that you see is the average of a bunch of averages. So a double bar. And I've drawn one on the top as a little bit larger. That's just my own stylistic preference. A lot of people don't do that. They're just the same equal size there. And this is oftentimes called the grand mean. And so what we have here in this concrete production chart, now we're with a slightly different recipe for the concrete, where we don't know the population mean, we don't know the population standard deviation. So what we do is we start plotting or gathering our data, and our center line then is our grand mean. Okay. Now, in order to be able to calculate then our upper and lower control limits, we have to deal with not knowing what the standard deviation of the population is. And so we have an estimator there too. Now you got to go back though and think about when the control chart was first formed. We didn't have the digital computer, and doing lots of calculations was a painful, long, tedious exercise. And if what you really were looking for was a simple way to quickly identify the potential that something of an assignable nature was happening to your process, then what you wanted was an easy way, quick way to process data. And one way to do that for spread is to estimate our standard deviation by the sample range. Right? And that's just the min and max that we have, and so we're going to end up taking the average of those ranges for each of our subgroups and dividing by a constant D2. Right, so our R bar is our average range from the subgroups. Right, so we have M subgroups, and in each one of those we have an individual range, which is just the max minus the min in that subgroup. And then D2 is a function of our sample size, and you'll find that listed in appendix of Montgomery-Runge and table Roman numeral 11. And that D2 value is going to be on the order of 1.128. Got one too many ones in there. 1.128 for n equals 2 up to 3.931 for n equals 25. Right, and unfortunately it's not a linear variation from 2 to 25, so you do have to actually go and look these up. But that's where they're going to be tabulated, is in that location. Right, so that's one way to get an idea. Quick and down and dirty, easy. This is simple to process. Right, and if you are always collecting the exact same number of samples in each subgroup, then your D number doesn't change any, and the R bar is very simple and easy to calculate. In many cases you can do that without a calculator, right? And so that gives you the estimate of your range, right? And so then our upper and lower control limits can be expressed in the following kind of fashion, and that is they will be centered at our grand mean, and then plus or minus a constant A2 times our R bar, where A2 is just 3 over D sub 2 square root of n. Right? So all we've done is we substituted in for sigma hat in for sigma x. So there's your R bar over D2 times square root of n. Your 3, we're just recollecting our terms. Sorry about that. There's your 3 over D2 square root of n. Now, in some areas of the world, they like to not use 3 sigma away from the mean as their control limit. They want to use something different. And of course, all you have to do then is just change that 3 into something else. That's where the 3 comes from, is that arbitrary choice to choose. It's sort of arbitrary, right? If we have a normal distribution, then the proportion of our population between plus or minus 3 sigma is 99.7% approximately. And that's really why we choose 3, that a vast majority of the, not just vast majority, almost all of the population should be within plus or minus 3 sigma. And so if you find something that's outside of that, that's why you think, hey, that's something that's out of control, something else is at work, that we don't ascribe to only just natural variation, because the odds of natural variation, the odds of natural variation causing that are so small that it's far more likely that there's something else at work. Right, so that's our general trend here, is in a general approach. Note that the symbols that I've used here is that this is an Xbar control chart. It is based upon the range. Right? We could also create a control chart for R itself. And you'll see in the Montgomery and Runge text the estimated values that we use there for the mean of R and the, so in a sense, the grand mean of R, so to speak, and also how we deal with the variation of R. And we do that because sometimes in certain processes it's not so much what's happening with the center, the body of the data, but rather it's the spread that we're trying to control and understand and monitor for the potential that other factors are coming into play. Right, now, what you also have in this example here, this is, I just showed you here conceptually how to go about doing this, but let's get into what some of the specific numbers are, and in particular calculating the upper control limit and the lower control limit for this specific case, and also the grand mean. Right, and so as we look at this data, a couple of things to keep in mind of how this data has been prepared for you, that we have our subgroup here in our first column, and then out of each subgroup we've got 3 cylinders that we've tested, and these are the concrete compression strengths in PSI. Right? And so this X bar here is directly just the average of those 3. The range for that subgroup then is just the max minus the min, And these are not listed in any particular order here, so it just turns out that the max is in column 1 in this first subgroup and the min is over in column 3, but go to the next one, you see that that's not the case anymore. And then of course the sample standard deviation here, and that is the same that we've seen before, that sum of the x value minus the sample mean quantity squared over the n minus 1 version square root of all of that is key, right? And just to make this crystal clear, range is max minus min, and x bar is your typical x bar equals 1 over 3 sum of the xi. Right, so that's what each one of these columns are. Now, if you're doing this using a tool such as Minitab or SPS and all kinds of other various ones, they'll do all these calculations for you. But if you're going to do this inside of, say, something like Excel, you have to build this yourself. Right? The grand mean down here then is found by the average of this whole entire column. That's our x bar, and then our r bar is our 1801, that's the average of this column, and our S bar is the average of all the sample standard deviations that we have along the way. Again, the key here is that m is equal to 25, that's a subgroup number, our n is equal to 3, and that's crucially important as you go look up values such as these constants. Now, I got a lot more constants than we need for this example as just a part of my spreadsheet that does this kind of statistical work. Ignore the A1 value here for a moment. That has not been verified yet. The A2 value, remember that A2 is equal to 3 over D2 square root of n. And if you put D2, which is read out of the table for n equal to 3, of 1.693 in here, n equal to 3, that equal to 1.693, you'll get 1.023 for that particular number. And that's the one that of course we need, right? And so our control limits then are found by upper control limit is equal to our grand mean plus A2 times R bar, and the individual numbers that we have here is that the grand mean is 5134.4, we have a A2 value of 1023, an R bar value of 1801, and that turns out to be then 6976.9 psi. And note that what we have down here is, sure enough, the upper control limit is 6977. Now, what I have down here, and the reason why it's formatted in this spreadsheet in this fashion, is that in this row I have the number of sigma that I'm interested in terms of the bounds, right? Because I'm thinking towards those zone rules and creating then the A, B, and C zones, and so I was interested in going ahead and calculating. I didn't plot that in that control chart, but that's why I have these other additional numbers. And again, all that you're doing is you're swapping out 3 with a 2, etc., etc. So that's how you can create the control chart for X bar, and for the control chart for the R bar, you would of course do something similar. The only reason I have the standard deviation calculated here is because another way to do this is not with X bar based upon R, but an X bar control chart based upon the standard deviation, which is what we'll do next.